Hello, this is me trying to find every single Polychora, but what exactly is a Polychora? Well, it's a four-dimensional polytope, but what is going to be used for the cells of these polytopes? Well, we need the platonic solids, and to connect them sustainably, we need to know the dihedral angles of them. Okay, let's go in order of dihedral angles in ascending order. Start with the tetrahedron. But first, we need a way to represent how many of these mean an edge. So let's represent that as a fire symbol thing. 3 is a 5 cell, 4 is a 16 cell, and 5 is a 600 cell. 6 requires hyperbolic geometry in 3 dimensions because the dihedral angles add up to more than 360. So let's move on to cubes. 3 is one many of you are probably familiar with, the 8 cell, although it's more commonly called a tesseract. Though something really interesting happens when you put 4 cubes at an edge. Because the dihedral angle of a cube is exactly 90 degrees, they can actually combine in an edge to create this infinite tessellation called the cubic honeycomb. Okay, time to jewel on to the octahedron. 3 is the 24 cell, and then that's it. And since the dihedral angles are just going to get bigger, the maximum number will be 3 or lower by this point. With dodecahedra, you can put 3 around an edge to create the 120 cell. However, with icosahedra, the maximum amount you could put on an edge without going hyperbolic is 2. However, since you need at least 3 polyhedra to create something, polychoron, this actually cannot work and therefore doesn't exist. There's also stuff like this which is nonsensical because you would somehow have to put tilings around an edge, which you can't really do. This means we have found every single regular polychora and even a regular 3D tessellation. Anyways, that's all from me today. Bye! Okay, I'm just going to move this hypersphere through the 4th dimension. Neat.